Okay, and then over here we have an extension y. Okay, so the dotted line I draw down here, I'm going to change the dotted line to green. Okay, so the dotted line down here is known as the equilibrium position. Okay, and then when I have an applied force, I put an F down here. Okay. Now, how does this look like in real life? Anyone? Right? So in real life, it looks like this. Okay. So you have a certain L naught. Right? You have a certain what? Cross-sectional area. And then when we put an applied force, this becomes what? L1. And then you have your what? Cross-sectional area under the applied force what? F. Yes or no? So what we have over here is our delta L. So delta L corresponds to L1 minus L0. So just now we used that ruler, yes or no? Right? And the ruler is like a what? Spring. How much force I apply to it, it can extend that much. Okay. Now, have you all seen free body diagram before? Okay, so if I were to have a metaphor, it's important for me to relate to you what the real world is like rather than we're going to throw in some formula and that's it. No. Okay, I don't do that to you. Other prof can do that, but I can do that to you. Okay. Now, if we have a structure on a side track, what is the boundary condition known as at point A and what is the condition at point B? Anyone? You learn this in mechanics. Yes or no? Tell me no, because I'll go after that. Did you all learn this in mechanics? Yes. Okay. So at point A, what do you call this? Pin. And at point B, what does it mean? Anyone? Roller. Beside the difference in spelling, what's the difference? If I call this X, and if I call this Y, what does it mean when it's pin? Anyone? Or just make a guess. Yes. At point where? At point A or point B? Okay, at point A, because it's pin, X is equal to 0, Y is equal to what? 0. How about point B? Point B, X is not equal to 0, Y is equal to what? 0. Yes or no? What if we call this, okay? So if this is our length, okay, this is our length. Okay, we just created a what? Boundary what? Conditions. Yes or no? So from here, how do you see this? Have you all walked under the bridge before? If in real life, how does a pin look like and how does a roller look like? When I was your age, I did not know. Okay, my prof is isn't off here. Right? How many of you drive? Stop by the highway sometimes, put on the signal light, go under the bridge. Okay? Don't do it between 3 to 4 because there is a time I'm going home. I think that is okay. Okay. Now, in real life, how does it look like? So if it's pin, I mean, the bridge are designed to rest on structure. So when it's pin, this is how it looks. And when it's a roller, this is how it looks. And then when I put my bridge on top, this is how it looks. Make sense? Yes or no? The boundary condition at point A is x is equal to 0, y is also equal to what? 0. The condition on point B, x is not equal to 0, y is equal to 0, because this can go what? Can go left and right, especially in Canadian weather. It's very important because you have hot summer, you can go up to 40, and we have cold winter, you got minus 40. Even more important in Canada than anywhere else in the world. We clear? If you're in Singapore, does not matter. Our temperature is sunshine or raining. Okay, right. So now you can visualize what a spring look like in real structure now. Okay. So anyone, any questions so far? No? Okay, right. So from here, as we mentioned before, the spring stiffness is the relationship between the applied force, right, and the extension. So on my x-axis, if I have x, and on our y-axis, sorry, I call it y. Sincerely apologize. So we tend to have a what? We tend to have a linear motion. Okay, we tend to have a linear motion, and over here, this is known as our delta F. This is known as our delta Y. Okay. So from here, we can formulate a expression where K, small k, okay, small k is equal to delta F over delta. So from here, we come up with a first expression where F is equal to K multiplied by Y, where F is our applied force, and X or Y is a change in length, and then K is the stiffness. And then when you look at units, this is in Newton or in pounds, okay? We are EDI, equity, diversity, inclusive. Yeah, we have to include this. And then we have meters. We also have inches. And over here, we have Newton per meter, or we can see this is pound per inch. Okay. Now, let us look into let us visualize this in a tensile test configuration. Okay, let us focus on a tensile. Anyone, any question up to this point? Are we clear? Okay. So if we were to visualize into a tensile test configuration, okay, so where we have, again, I drew this before. This is our rod with no force applied. So again, this is our L naught. And then on the other side, we apply a load. This is our L1 with a load P. So under the elastic region, the material will behave under Hooke's law. So what do I mean by Hooke's law? Can you remember Hooke's law? Yes or no? Don't forget Hooke's law. Okay. So it's a linear relationship between stress and strain in the elastic what? Region. So when we apply Hooke's law, okay, the gradient over here, any idea what's the gradient over here called? Anyone? It's known as what? So from here, we have the expression. Okay. Now, those of you that attend my class today, before my class, what class do you have? Nothing? Or you have nothing? Say it again. Okay, so you have something. So I will start class usually 2 minutes after 9:30, just to let you know. Good to see you. Have fun. Don't be so miserable. Are you okay or no? I'm worried now. Okay. You okay? Okay, go home, go home. Not go home, go for your next class.
Go on. I won't be here for the first midterm. I'm going to be at ASI